The Milky Way is so vast that even the most powerful numbers we can imagine struggle to capture its immensity. Our solar system, with its planets, moons, and the Sun that feels impossibly large to us, is nothing more than a microscopic speck within this cosmic giant. When we ask the question, how big is our galaxy? We aren't simply asking about distances we could one day travel. We are pushing against the very limits of human comprehension. The Milky Way is not just wide, it's layered with invisible structures, crowded with billions of stars, and wrapped in a halo of mystery that stretches far beyond what we can see. To even begin to grasp its scale, we must let go of everyday measures like kilometers or miles. The size of the Milky Way stretches so far beyond what we can imagine that understanding it is less about knowing a number and more about confronting the vastness of existence itself. It is our home, but also a reminder that home is bigger than anything we can touch, bigger than anything we can truly picture in our minds. The Milky Way is more than just the glowing band of light we sometimes glimpse stretching across the night sky. It is a galaxy, a colossal, gravitationally bound system containing stars, planets, moons, asteroids, nebulae, gas clouds, dust, black holes, and dark matter. To put it simply, everything we have ever known, every star we can see with the naked eye, and every corner of the observable universe we can explore without leaving our galaxy is part of this vast structure. When astronomers classified the Milky Way, they determined it to be a barred spiral galaxy, meaning it has a central elongated bar-shaped structure of stars, from which the spiral arms stretch outward like curved ribbons. This bar is an essential feature, acting almost like a backbone that helps funnel gas toward the galactic center, fueling star formation and activity around the supermassive black hole that resides there. The spiral arms are perhaps the most striking feature of our galaxy's design. These arms are not solid objects but vast regions where gas, dust, and stars are more densely concentrated, giving them a bright, sweeping appearance. Within these arms lie countless star-forming nurseries, regions where new suns are being born from collapsing clouds of gas and dust. These nebulae, such as the Eagle Nebula or the Orion Nebula, are like cosmic cradles, shaping the future generations of stars and planetary systems. And yet, despite their beauty, these arms are only part of a far larger framework. The Milky Way is structured into multiple major and minor spiral arms, with our solar system nestled in one of the smaller arms known as the Orion Arm or Orion's Spur. This makes our home a relatively quiet and less densely packed region of the galaxy, safe from the chaotic heart of the Milky Way, where stars crowd tightly together and gravitational forces create extremes unimaginable to human experience. From the Orion Arm, we orbit the galactic center, along with billions of other stars, in a vast cosmic dance that has been going on for billions of years and will continue for billions more. At the very core of the Milky Way lies the Galactic Bulge, a densely packed region of stars, dust, and gas, centered around the supermassive black hole, Sagittarius A. This bulge is not flat like the disk of the galaxy, but spherical in shape, giving the Milky Way a three-dimensional complexity that makes it even harder to visualize. The bar structure connects this bulge to the spiral arms, acting like a highway for material to flow inward, fueling activity at the center and driving the evolution of the galaxy itself. Beyond the disk and the spiral arms is the galactic halo, a vast spherical region filled with old stars, globular clusters, and an unseen but immensely significant component, dark matter. While the disk of the Milky Way contains the most visible stars, the halo stretches much farther, acting like an invisible bubble that defines the galaxy's full size and gravitational influence. Within this halo are ancient star clusters, remnants from the early days of galactic formation, making it almost like a fossil record of our galaxy's history. Nebulae, scattered across the galaxy, are another defining feature of the Milky Way. These clouds of gas and dust are both the graveyards and the birthplaces of stars. Some nebulae, like planetary nebulae, are formed when dying stars expel their outer layers into space, creating hauntingly beautiful shells of gas. Others, such as emission nebulae, glow brightly as radiation from nearby young stars excites the gas within them. Then there are dark nebulae, which absorb and block light, creating vast voids that look like holes cut out of the starlit sky. Each type of nebula contributes to the cycle of matter that fuels the galaxy. Stars are born, live out their lives, die, and return material back into the galaxy, enriching the interstellar medium for new generations of stars and planets. The Milky Way is also home to countless planetary systems, and thanks to modern telescopes, we now know that planets are not rare at all, but common. Billions of them orbit the stars scattered across the galaxy, and many of them may be rocky worlds like Earth or gas giants like Jupiter. Some may orbit in the habitable zones of their stars, where liquid water could exist, raising the tantalizing possibility that life may not be confined to our small corner of the galaxy. This realization expands not only our sense of the Milky Way's physical size, but also its potential richness and diversity in terms of environments and possibilities. When we consider the Milky Way as a whole, it is not a flat disk floating in space, but a layered and dynamic structure. It has a thin disk where most stars and gas lie, a thicker disk populated by older stars, a central bulge dominated by the black hole, and a halo extending outward far beyond what we can see. It rotates, evolves, and interacts with smaller galaxies around it. Our Milky Way is even actively consuming smaller dwarf galaxies, pulling them in and incorporating them into its own structure, adding to its mass and complexity. This process is part of how galaxies grow, not in isolation, but through cosmic mergers and interactions. In terms of sheer composition, the Milky Way is a balance of visible matter, stars, gas, planets, and invisible matter, which we call dark matter. Dark matter does not emit light, yet it exerts gravitational influence, holding the galaxy together and explaining why the outer regions of the disk rotate faster than visible mass alone would allow. Without dark matter, the Milky Way as we know it could not exist in its current form. When we try to describe the size of the Milky Way, ordinary units like kilometers or miles simply collapse under the weight of the numbers involved. Distances in space are so vast that even the largest numbers we use on Earth quickly become meaningless. For example, the Earth is about 40,000 kilometers around its equator, and the Moon is only 384,000 kilometers away. Figures that feel large, but still imaginable. Yet the nearest star beyond our Sun, Proxima Centauri, is over 40 trillion kilometers away. Writing that number down makes sense mathematically, but it doesn't help our human minds grasp the scale. This is why astronomers rely on a special unit, the light year. A light year is not a measure of time, but of distance. It represents how far light can travel in 1 year. Since light moves at a speed of about 299,792 kilometers per second, in a single second, it could circle the Earth about 7.5 times. Over the course of a year, this amounts to nearly 9.46 trillion kilometers. That number, while still massive, becomes a much more practical yardstick for measuring cosmic distances. Instead of saying Proxima Centauri is 40 trillion kilometers away, we say it is 4.24 light-years distant. Suddenly, the incomprehensible becomes slightly more manageable. To truly appreciate the immensity of scale within the Milky Way, light years are essential. Our galaxy is not thousands, not millions, but over 100,000 light-years across. This means that even if you were traveling at the speed of light, the fastest speed the universe allows, it would take you 100,000 years just to cross from one end to the other. Nothing in human experience even comes close to this kind of scale. By comparison, our entire solar system, from the Sun to the outer edges of the Oort cloud, measures only about 2 light-years in diameter at most. That's an infinitesimal sliver compared to the galaxy itself. Light-years also help us understand not just distances, but time. When we look out into the galaxy, we aren't seeing stars as they are now. We are seeing them as they were when their light first began its journey to us. For example, a star 1,000 light-years away is seen by us as it was 1,000 years ago. In this sense, the Milky Way is not only vast in space, but also stretches backward in time, with every star offering a glimpse into the past. This adds another layer to the concept of immensity, because to measure distances in the galaxy is also to measure the history of light itself. The need for light years becomes even more apparent when we consider that many features of the Milky Way, like spiral arms, the galactic bulge, or the halo, span tens of thousands of light years. Even the thickness of the galactic disk, which may sound relatively small compared to its width, is still about 1,000 light years thick. To describe this in kilometers would mean rattling off endless strings of digits that no one could hold in their memory. But with light years, we can reduce those mind-crushing numbers to something we can discuss and compare, even if they still remain far beyond everyday intuition. This is why, when talking about galactic size, astronomers almost exclusively use light years. It's not just convenient, it's necessary. Without this unit, the language of cosmic distances would be so bloated with numbers that even professionals would struggle to keep track. Light years give us a way to scale the infinite, to create a bridge between the human mind and the enormity of the galaxy. And yet, even with this tool, the scale of the Milky Way still overwhelms. Saying something is 100,000 light-years wide may sound more digestible than 9.46 trillion kilometers times 100,000, but it still conveys the same staggering truth. Our galaxy is beyond anything we can truly picture. The light year doesn't shrink the galaxy. It simply gives us a way to talk about it without drowning in zeros. When we finally ask the question, how wide is the Milky Way? The answer reveals the staggering immensity of our galactic home. Astronomers estimate that the Milky Way stretches across roughly 100,000 to 120,000 light-years in diameter, meaning that if you could travel at the speed of light, it would take you more than 100,000 years just to get from one edge to the other. That figure alone is almost impossible for the human mind to process, but it's worth breaking it down to truly grasp what it represents. 1 light-year equals about 9.46 trillion kilometers. If the galaxy is around 100,000 light-years wide, that means it spans about 946 trillion kilometers across, a number so incomprehensibly large that it collapses into abstraction. But here's where things get even more fascinating. The figure of 100,000 to 120,000 light-years is not a fixed number, but an estimate. As our technology improves, we continue to refine this measurement. Some studies, especially those that take into account the outermost stars and streams of gas and dust, suggest that the Milky Way may actually be closer to 150,000 to 200,000 light-years across if you include its faint outermost regions. This demonstrates that the galaxy doesn't have a sharp edge like a solid object. Instead, it gradually thins out, with stars, clusters, and streams of material stretching farther and farther into intergalactic space. The true boundary is difficult to define, making the diameter of the galaxy a concept that is as much about how we choose to measure it as it is about an absolute edge. The main disk of the galaxy, the part we typically picture when we imagine the Milky Way's spiral shape, is what falls within that 100,000 to 120,000 light-year range. This disk is the densest region, containing the majority of the stars, planets, gas, and nebulae that we associate with the Milky Way. Yet beyond this disk lies the extended stellar halo, globular clusters, and dark matter that push its influence even farther. When scientists account for these outer structures, the galaxy becomes not only wider, but also much more massive than the initial diameter suggests. To put this into perspective, think about our place inside this vast system. The solar system sits about 27,000 light-years from the galactic center, not too close to the dangerous, crowded middle, and not too far out in the sparse outer regions. From our position, we can only see part of the Milky Way in great detail, because dust and gas obscure our line of sight through the galactic disk. It's a bit like trying to measure the size of a massive forest while standing deep inside it. You can see the trees nearby, but to estimate the size of the entire forest, you need tools, models, and indirect evidence. That is exactly what astronomers face when trying to measure the Milky Way's diameter. The figure of 100,000 to 120,000 light-years is derived from a combination of observations, including mapping the distribution of stars, studying the spiral arms, and measuring the movements of distant objects within the galaxy. For example, surveys like the Gaia mission, which maps the positions and motions of over 1 billion stars, give us a clearer idea of how far the disk extends. Meanwhile, radio telescopes that observe hydrogen gas, which permeates much of the galaxy, reveal the structure of the outer arms and the galactic disk, stretching farther than the densest regions of stars. One of the biggest challenges in determining the galaxy's true diameter is that stars do not end at a sharp boundary. Instead, the stellar density gradually decreases until, at some point, it becomes indistinguishable from intergalactic space. Some astronomers argue that the Milky Way's stellar disk might be closer to 180,000 light-years across when faint outer streams of stars are included. Others propose that the dark matter halo, which envelops the entire galaxy, could extend over 1 million light-years in diameter, though this is not the visible size of the galaxy as we usually describe it. This means that the Milky Way's diameter, depending on how you define its edge, could vary enormously, and our understanding of it continues to evolve with every new observation. When compared to other galaxies, this diameter makes the Milky Way a fairly large galaxy, though not the largest. Dwarf galaxies, for instance, can be just a few thousand light-years across, making the Milky Way hundreds of times larger in diameter. On the other hand, giant galaxies like IC 1101 dwarf the Milky Way, stretching over 6 million light-years across. Yet the Milky Way is still considered massive in its own right, housing hundreds of billions of stars within its enormous width. Its size places it firmly in the category of large spiral galaxies, on par with other giants such as the Andromeda galaxy, which itself is about 220,000 light-years across. The immensity of the Milky Way's diameter also becomes clear when we consider time. If we could travel across the galaxy at a much slower, human-conceivable speed, say at the pace of the fastest spacecraft ever built, it would still take billions of years to cross it. The Voyager probes, for example, which have been traveling through space for over 4 decades at tens of thousands of kilometers per hour, haven't even come close to leaving our solar system, a region that itself is microscopic compared to the Milky Way's total width. This comparison underscores just how unfathomable the galaxy's diameter is in practical terms. What makes the diameter even more incredible is that within this vast width lies an unimaginable variety of cosmic environments. From dense star clusters near the center to quiet stretches of the outer disk where stars are sparse, The Milky Way's size is not just an abstract number, but a measure of its diversity. Across 100,000 light-years, conditions vary so greatly that one part of the galaxy can be bursting with newborn stars, while another has only the dim remnants of ancient stellar populations. The diameter encompasses regions where supernovae light up the night, and others where stars have long since burned out, leaving behind white dwarfs, neutron stars, and black holes. When we talk about the Milky Way's size, most people focus on its width, the enormous 100,000 to 120,000 light-years across. That makes it feel almost endless. But what often surprises people is that, for all of that sprawling distance, the galaxy is actually relatively thin. The disk of the Milky Way, where the majority of its stars, nebula, and gas clouds reside, is only about 1,000 light-years thick on average. To put that in perspective, if the Milky Way was scaled down to the size of a giant dinner plate about a meter wide, its thickness would be no greater than a sheet of paper. This comparison helps us visualize why astronomers describe the galaxy as a flat, disk-like structure. It's wide and expansive, yet strikingly compressed in terms of vertical depth. This thinness is not accidental, but a natural outcome of galactic dynamics. Galaxies like ours rotate, and as stars and gas orbit the center, their combined gravity and motion gradually flatten the system into a disk shape. Much like pizza dough spinning on a chef's hands stretches into a flat circle, the Milky Way has been shaped into a disk by billions of years of rotation. The thin structure of the disk also reflects the balance of gravity pulling inward and the angular momentum of stars and gas pushing outward. It's a cosmic balancing act that gives the galaxy its characteristic shape. Of course, the galaxy's thickness is not uniform everywhere. The thin disk, which contains most of the Milky Way's younger stars, open clusters, and star-forming regions, averages around 600 to 1,000 light-years in thickness. Then there's a thicker disk, a population of older stars that extends farther above and below the galactic plane, reaching about 2,000 to 3,000 light-years thick. This thicker disk is less densely populated, but holds important clues about the galaxy's early history, as it contains stars that are billions of years old and formed during the galaxy's more turbulent youth. When we look at the Milky Way in the night sky, the thinness of the disk is what gives us that glowing band of light stretching across the darkness. What we're seeing is the combined glow of billions of stars concentrated into a relatively narrow plane. If the galaxy were thicker, that band would appear much broader and fuzzier. Instead, the slim structure creates a sharp contrast between the bright galactic plane and the darker regions of space above and below it. This visual distinction is one of the most striking features of our view from inside the galaxy. Despite being thin compared to its width, the disk's thickness is still unimaginably large by human standards. 1,000 light-years translates to about 9.46 quadrillion kilometers. If we could travel straight up or down from the galactic plane at the speed of light, it would still take a millennium to escape the disk entirely. That's longer than all of recorded human history by a factor of 5. This shows that even the thin parts of the galaxy are far beyond what our minds can comfortably imagine. The thinness also creates a kind of layered structure within the Milky Way. Stars and nebulae hug the galactic plane closely, while above and below it, the density drops dramatically. This is why astronomers can peer out of the disk in directions perpendicular to it and see far into intergalactic space, where there are fewer stars and less dust to obscure the view. These windows above and below the galactic plane are vital for studying galaxies beyond our own. If the Milky Way were thicker and dustier, our view of the universe outside would be much more limited. Interestingly, the thin disk is not perfectly flat. It has a warp, a gentle bending or twisting of the galactic plane. Observations show that the Milky Way's disk is slightly curved, possibly due to gravitational interactions with nearby satellite galaxies, such as the Magellanic Clouds, or the uneven distribution of dark matter in the halo. This warp means that the disk is not just thin, but also dynamic, constantly shifting over cosmic timescales. Such warping isn't unique to the Milky Way. Other spiral galaxies observed by telescopes also show similar bends in their disks. The thickness of the galaxy also plays a role in star populations. Younger stars, including hot blue giants and newborn clusters, are found primarily in the thin disk, where gas and dust are plentiful. Meanwhile, older stars, long past their prime, are scattered in the thicker disk, reflecting an older, less active phase of the galaxy's history. This distribution tells astronomers a great deal about how the Milky Way has evolved, showing a layered timeline encoded into its very structure. Another fascinating consequence of the galaxy's thinness is how it amplifies our sense of smallness. The solar system, orbiting within the Orion Arm, is tucked neatly into this thin layer. We are so deeply embedded in the galactic disk that if you were to look straight up or down, you'd still see countless stars stretching thousands of light years before finally reaching emptiness. Yet, compared to the horizontal span of the galaxy, our vertical neighborhood is just a razor-thin slice. This makes the solar system feel even more insignificant, like a speck within a paper-thin line drawn across a vast canvas. When you combine width and thickness, the overall shape of the Milky Way resembles a flattened disk with a bulging center, often compared to a fried egg when seen edge-on. The yolk is the galactic bulge, while the white is the thin disk spreading outward. This image, while simple, gives us a surprisingly accurate picture of the galaxy's geometry. From afar, the thinness of the disk would be even more obvious, as the galaxy would appear like a shining, flattened oval against the black backdrop of space. At the very heart of the Milky Way lies something extraordinary, something that shapes the very character of our galaxy, the central bulge. This bulge is a densely packed region filled with stars, dust, and gas, creating a glowing hub of activity unlike any other part of the galaxy. If the galactic disk can be compared to a sprawling, thin pancake of stars, the bulge is the swollen, luminous center that rises out of it, a beacon of concentrated brilliance. Stars here are far more crowded together than in our region of the galaxy. In some areas, the night sky would be ablaze with thousands of suns, so close and so bright that darkness as we know it might barely exist. But this isn't just a random gathering of stars. At the very core of the bulge sits Sagittarius A, the supermassive black hole that anchors the galaxy. With a mass of about 4 million suns, it exerts a gravitational pull strong enough to hold the Milky Way together. Though it is invisible directly, the stars orbiting around it tell us of its presence, moving at speed so great they can only be explained by the immense gravity of something so compact and powerful. The bulge, then, is not only a collection of ancient stars, but also the visible footprint of this invisible giant, the heart that beats at the center of our galactic home. The stars in this bulge are, for the most part, older than the stars scattered throughout the spiral arms. These ancient suns were born in the galaxy's earliest days, their light having burned for billions of years, carrying with them the history of cosmic events long past. Their orbits are not neat circles like many stars in the disk, but rather more chaotic and elliptical, giving the bulge its puffed-up, spherical appearance. Dust and gas are also trapped here, swirling and feeding bursts of star formation near the core, though on a scale different from the serene, patterned beauty of the arms. When astronomers peer into this dense region, they encounter not only dazzling beauty, but also profound challenges. The thick clouds of interstellar dust obscure much of the light from the bulge, making it invisible in ordinary optical wavelengths. To study it, scientists must rely on infrared telescopes, radio observations, and other tools that can pierce through the veil of cosmic dust. What they uncover is a dynamic environment, stars whipping around at incredible speeds, bursts of high-energy radiation, and structures shaped by the influence of Sagittarius A. This central activity is sometimes described as the galaxy's engine room, a place where unimaginable forces are constantly at play. It's humbling to realize that while we orbit calmly in one of the quieter spiral arms, the core of our galaxy is a realm of extremes. If Earth were closer to the bulge, life would be drastically different, perhaps even impossible. The radiation levels, the gravitational turbulence, and the sheer density of stars would create a cosmic environment hostile to life as we know it. Yet, paradoxically, this violent and energetic heart is also what binds the Milky Way together, keeping its spiral arms and stars in place as it spins majestically through the universe. The galactic bulge is both a relic of the Milky Way's ancient beginnings and a dynamic, living part of it, continually shaped by gravity, star formation, and the influence of the black hole. It reminds us that our galaxy is not static, but alive with movement and change. As scientists continue to probe deeper into its mysteries, every discovery reveals not just the story of a central cluster of stars, but the deeper truth of how galaxies form, evolve, and endure across cosmic time. Surrounding the shining disk of the Milky Way, beyond the spiraling arms, and even beyond the glowing bulge at the center, lies something that is far less visible but no less important: the galactic halo. To most of us, when we imagine the Milky Way, we picture the flat spiral of stars and dust, glowing brightly against the night sky. But this view is incomplete. The disk, as spectacular as it looks, is only part of the story. Encasing it all is a vast, ghostly sphere that extends far beyond the regions we normally think of as the galaxy. This halo is made of scattered stars, ancient clusters, and, most significantly, an invisible material known as dark matter. Without this halo, the Milky Way as we know it could not exist. The halo is immense. While the galactic disk measures about 100,000 to 120,000 light-years across, the halo stretches out to distances perhaps 10 times larger. Some estimates suggest that the dark matter halo could extend more than 1 million light-years from the center of the Milky Way, reaching halfway to our nearest galactic neighbor, Andromeda. That means the halo is not only bigger than the visible galaxy, it's the dominant structure that defines its true shape and gravitational influence. If we could somehow see the halo with our eyes, the Milky Way wouldn't look like a thin, glowing band across the sky, but instead like a vast, faint sphere engulfing everything. At the edges of the halo float stars that don't conform to the familiar spiral pattern. These stars are often relics of smaller galaxies that were captured and torn apart by the Milky Way's gravity, their remnants scattered like crumbs around the edges of a feast. In fact, some of the halo's most ancient residents are globular clusters, densely packed balls of stars, many of them over 12 billion years old. These clusters orbit the galaxy in wide, sweeping paths, moving through the halo like time-worn satellites. Each cluster contains hundreds of thousands of stars, glowing reminders of the Milky Way's earliest days. By studying them, astronomers gain insights into how our galaxy assembled itself, devouring smaller galaxies and growing into the giant it is today. But what truly defines the halo isn't just the scattered stars or clusters, it's the dark matter, the mysterious, invisible substance that outweighs all the visible stars, gas, and dust combined. Dark matter doesn't emit or absorb light, which means we can't detect it directly. Its presence is known only through its gravitational effects. Without dark matter, the Milky Way simply wouldn't hold together. The stars in the outer edges of the galaxy orbit far too fast to be bound by the gravity of visible matter alone. Something unseen is keeping them from flying off into intergalactic space, and that something is the vast reservoir of dark matter in the halo. Scientists estimate that dark matter makes up about 85% of the Milky Way's total mass. That means the glowing disk we see, the stars, planets, nebulae, and even Sagittarius A at the center, is only a small fraction of what the galaxy truly is. The real bulk of the Milky Way lies hidden, silently shaping the motion of stars and determining the galaxy's fate. The halo's dark matter acts like a cosmic glue, holding everything together as the galaxy spins. What's particularly fascinating is that the halo is not uniform. Studies suggest it may be lopsided, stretched, or even peppered with ripples and clumps, scars from collisions with other galaxies. Every time the Milky Way swallowed a smaller galaxy, the event left its mark on the halo, disturbing its structure and scattering streams of stars across it. Astronomers have mapped some of these stellar streams, long ribbons of stars, tracing out the paths of long-lost galaxies that were once whole before being absorbed. These streams act like footprints in the sand, telling the story of the Milky Way's growth through cosmic cannibalism. The halo is also a place of mystery. We know it's there, but we don't know exactly what it looks like, nor do we fully understand its composition. Could dark matter be made of undiscovered particles? Could the halo harbor faint, long-dead stars, or even rogue planets drifting through the void? These are questions that continue to drive research. One thing is certain: the halo is not an empty shell. It is dynamic, active, and absolutely essential to the Milky Way's survival. If the disk is the stage where the drama of star formation and life unfolds, then the halo is the unseen framework that makes the entire performance possible. Without it, the spiral arms would not hold, the stars would scatter, and the galaxy would lose its structure. The halo, in its quiet invisibility, is the backbone of the Milky Way, a reminder that not all of reality is visible to our eyes. In fact, most of what exists in our galaxy is invisible, hiding in plain sight. The more we learn about the halo, the more it reshapes our understanding of what a galaxy truly is. A galaxy is not just the stars we see shining at night. It is not just the nebulae, the planets, or even the black holes. It is a system far greater, stretching beyond what light reveals, anchored in an ocean of dark matter and ancient stars that extend into the depths of space. The halo reminds us that the Milky Way is not only vast in size, but vast in mystery. The sheer number of stars within the Milky Way is nothing short of staggering. Estimates place the total somewhere between 100 and 400 billion stars, each with its own story, its own system, and, in many cases, its own planets. These stars are not just distant points of light. They are colossal furnaces of nuclear fusion, creating the energy that lights up the galaxy and drives the chemical evolution of the universe. When we try to comprehend the size of the Milky Way, it's not enough to consider distances alone. Its immensity is amplified by this astronomical population of stars, each contributing to the mass, gravity, and luminous presence of the galaxy. Even the lower estimate of 100 billion stars means that for every human alive today, there are roughly 12,000 stars in the galaxy, emphasizing how overwhelmingly vast and populated our cosmic neighborhood really is. These stars are not evenly distributed. Some regions, such as the central bulge, are densely packed with millions of stars per cubic parsec, creating environments where gravitational interactions are frequent and chaotic. In the spiral arms, stars are more spread out but still abundant, forming clusters, associations, and sometimes entire star-forming regions brimming with young, bright stars. The halo contains fewer stars scattered widely across immense distances. But even there, ancient stars and globular clusters add to the total count. This means that the Milky Way is not only vast in terms of kilometers or light years, but also in terms of the sheer number of stellar objects it contains. A living, dynamic ecosystem of stars, each contributing to the gravitational architecture of the galaxy. The variety among these stars is also immense. There are tiny red dwarfs, the most common type of star, faint and long-lived, burning slowly for trillions of years. There are massive blue giants, which shine with incredible intensity but exhaust their fuel in just millions of years. There are yellow stars like our Sun, offering a stable energy output over billions of years, making planetary systems like ours possible. Among the 100 to 400 billion stars, there are neutron stars, white dwarfs, and even black holes, remnants of massive stars that have ended their lives in spectacular fashion. This diversity means that the galaxy is not a uniform expanse of stars, but a complex tapestry of stellar types, ages, and evolutionary stages. Beyond the stars themselves, this immense population has profound implications for the galaxy's structure and dynamics. Each star contributes gravitationally to the overall mass of the Milky Way, helping to shape the rotation of the disk, the bulge, and the halo. The interactions between stars, especially in dense clusters, can trigger new star formation or even alter the paths of existing stars, creating streams and ripples across the galaxy. Some stars, once part of dwarf galaxies, have been captured into the Milky Way, adding to the total population and gradually reshaping the galaxy over billions of years. Every single star, no matter how faint or distant, is part of the web that keeps the galaxy together. The number of stars also underscores the impossibility of truly picturing the Milky Way in its entirety. When we look up at the night sky and see perhaps a few thousand stars with the naked eye, we are only glimpsing a tiny fraction of the galaxy's population. Most stars, even nearby ones, are too faint to see without telescopes, and countless others are hidden by dust and gas in the disk. Modern surveys, such as those conducted by the Gaia satellite, have mapped over 1 billion stars, yet this is still only a fraction of the Milky Way's total. To imagine 100 to 400 billion stars is to stretch the mind to its limits, to think in terms that transcend everyday experience, and to confront the true immensity of the galaxy's population. The staggering number of stars also emphasizes how much more the Milky Way is than just a distance across space. The galaxy's size is not only measured in light years or kilometers, but in the richness of its contents. Every star represents a gravitational anchor, a source of energy, and a potential host to planets, asteroids, and perhaps life. When we combine this stellar abundance with the Milky Way's vast diameter, we begin to see the galaxy not as a simple structure floating in space, but as a teeming, dynamic ecosystem spanning tens of thousands of light years and containing an unimaginable number of suns, each burning steadily in a delicate cosmic balance. Even considering only the lower estimate of 100 billion stars, it's almost impossible to count them all in a human sense. Yet astronomers attempt to understand the galaxy statistically, categorizing stars by type, mass, and location, building models that help explain everything from the spiral structure to the motion of distant stars. Each new star discovered adds a piece to this puzzle, refining our understanding of the Milky Way and its extraordinary contents. And when we consider the higher estimates of 400 billion stars, the complexity multiplies. The interactions, collisions, and gravitational influences among stars become a symphony of cosmic forces that have shaped the galaxy over billions of years. In essence, the Milky Way's size is not just about distances or diameters. It is about sheer abundance. The galaxy is an immense collection of luminous objects, stretching across the vastness of space, and every star contributes to the gravitational dance that keeps the galaxy coherent. Its immensity is therefore both physical, in terms of the space it occupies, and numerical, in terms of the number of stars it contains. To truly grasp the Milky Way's scale, we must think of it not only as a 100,000 light-year wide disk, but also as a galaxy containing hundreds of billions of stellar furnaces, each a miniature sun, each contributing to the grand structure that surrounds us. When we step back and try to place our solar system within the vast expanse of the Milky Way, the scale becomes almost absurd. Our solar system, which feels infinite to us in our everyday lives, is minuscule when compared to the galaxy that hosts it. From the Sun to the outer edge of the Kuiper Belt, the solar system spans roughly 100 astronomical units, about 15 billion kilometers. Even if we include the hypothetical Oort cloud, which may stretch up to 2 light-years from the Sun, this distance is still microscopic relative to the galaxy's diameter of over 100,000 light-years. To visualize it, imagine the entire Milky Way as a football field. In that analogy, the solar system would be roughly the size of a single grain of sand placed somewhere on the field. Its tiny presence emphasizes just how inconsequential we are in terms of galactic scale. And yet, paradoxically, it's within this tiny speck that all known life exists. This comparison is even more striking when we consider distances in terms of light. Light takes about 8 minutes to travel from the Sun to Earth, a distance of 150 million kilometers, known as 1 astronomical unit. In contrast, it would take over 100,000 years for light to cross the Milky Way. This means that every journey across the galaxy, from one edge to the other, involves distances that dwarf even the farthest reaches of our own solar system. Our planets, asteroids, and distant icy bodies occupy an almost negligible fraction of space, orbiting within the gravitational cocoon of the Sun, while the galaxy itself spins and rotates, a colossal system of stars and dark matter extending thousands of times beyond our local neighborhood. The sheer number of stars makes the solar system's smallness even more apparent. The Sun, one star among hundreds of billions, is part of the Orion Arm, a relatively minor spiral arm of the galaxy. Even within this arm, nearby stars are separated by several light-years, distances so large that traveling between them at the speed of current spacecraft would take tens of thousands of years. And yet, this tiny neighborhood is all we can directly reach and observe in detail. Compared to the expanse of the Milky Way, our solar system is but a single point, a tiny beacon of matter in a galaxy brimming with stars, nebulae, and planetary systems we can scarcely imagine. Another way to think about it is to imagine the Milky Way's spiral arms. These arms extend for tens of thousands of light-years, curving and twisting outward from the central bulge. Within them are billions of stars, clustered into star-forming regions, clusters, and associations. Our solar system resides quietly on the inner edge of the Orion Arm, far from the chaos of the dense galactic core. To traverse even one spiral arm at the speed of light would take tens of thousands of years, a journey that makes the solar system's size feel like nothing more than a pinpoint on a cosmic map. The galaxy is alive with structure, and we occupy a mere corner of it. The Oort cloud provides a useful analogy to further highlight the contrast. This distant shell of icy bodies, extending up to 2 light-years from the Sun, represents the outermost boundary of our gravitational domain. Even this seemingly enormous region is only a fraction of 1% of the galaxy's diameter. If the Milky Way were a vast city, The solar system would be like a single room tucked away on a quiet street, surrounded by billions of other rooms, neighborhoods, and sprawling districts that we will never see in their entirety. This makes it difficult to overstate how tiny we truly are in the galactic context. Despite this immense disparity in scale, the solar system's smallness is precisely what makes it a coherent and stable environment for life. If the Sun were part of a denser region, like the central bulge, its planets might be destroyed by gravitational interactions or intense radiation from nearby stars. Its location in a relatively calm spiral arm allows the solar system to persist for billions of years, providing the stable conditions necessary for life to emerge and evolve. In this sense, the tiny scale of our solar system within the galaxy is not a limitation, but a privilege, allowing us to exist in an otherwise chaotic cosmos. The contrast between the solar system and the Milky Way also underscores the human challenge of exploration. While we have sent spacecraft like Voyager and New Horizons to the edge of our solar system, these missions have barely scratched the surface of interstellar distances. Traveling even to the nearest star, Proxima Centauri, located 4.24 light-years away, would take tens of thousands of years with current technology. And yet, the Milky Way spans tens of thousands of times that distance. In terms of exploration and presence, our solar system is a tiny, isolated outpost floating within an unimaginably vast and complex environment. Visualizing this tiny scale helps put human history and achievement into perspective. All of human civilization has developed on Earth, a planet orbiting one star in this vast galaxy for just a fraction of a cosmic second. Yet, from this tiny vantage point, we have managed to peer across light years, map the galaxy's spiral arms, and even identify distant stars and planets. In essence, the solar system is our personal laboratory, a minuscule island in the grand ocean of the Milky Way. Its smallness highlights both our fragility and our curiosity, showing how much we have learned from such a tiny slice of the universe, while simultaneously emphasizing how much more there is to explore. Even in terms of volume, the contrast is overwhelming. The Milky Way is a flattened disk over 100,000 light-years wide and about 1,000 light-years thick. Our solar system, even considering the farthest reaches of the Oort cloud, occupies a sphere barely a few light-years in diameter. The galaxy's total volume is therefore millions of times larger than that of our solar system. Each planet, each asteroid, and each comet exists within a space that, on a galactic scale, is almost negligible. Yet, it is precisely this tiny environment that has given rise to life, intelligence, and the capacity to wonder about the galaxy itself. Understanding the solar system's minuscule scale also gives context to the challenge of mapping the Milky Way. From our tiny perch, we attempt to measure distances, trace spiral arms, and infer the presence of dark matter, all while embedded within one of its arms. Every calculation and observation is made from a fraction of a single light-year across, while the structure we aim to understand spans 100,000 light-years. The contrast between the minuscule scale of our solar system and the colossal breadth of the Milky Way highlights not only the galaxy's immensity, but also the ingenuity of human science in attempting to comprehend it. Even when we consider the Milky Way in terms of the speed of light, the scale remains almost incomprehensible. Light, traveling at an astonishing 299,792 kilometers per second, is the fastest thing in the universe, capable of circling the Earth 7.5 times in a single second. Yet, even at this ultimate cosmic speed, it would still take roughly 100,000 years to traverse the galaxy from one edge of the disk to the other. To frame this in human terms, the entire span of recorded human history, from the earliest civilizations through the modern age, is just a blink compared to the time it takes light to cross the Milky Way. This perspective forces us to confront the enormity of the galaxy in a way that distances alone cannot convey. It's not just wide, it is immeasurably vast in terms of time as well as space. The speed of light perspective also helps us understand why observing the galaxy is so complex. When we look at stars in the Milky Way, we are not seeing them as they are now, but as they were thousands or even tens of thousands of years ago, depending on their distance. A star 10,000 light-years away is showing us light that began its journey 10,000 years before the birth of our modern civilization. When we observe the edge of the galactic disk, we are looking at regions whose light started traveling toward us long before recorded history even existed, offering a glimpse into the galaxy's distant past. The sheer time it takes light to cross the Milky Way means that our view of the galaxy is a patchwork of ancient snapshots stitched together across tens of thousands of years. To truly comprehend this, consider the journey of light across the Orion Arm, the spiral segment in which our Sun resides. The arm spans tens of thousands of light-years, yet light itself requires tens of millennia to travel from one end to the other. This means that any events occurring at the far reaches of our spiral arm, whether starbirths, supernovae, or collisions between gas clouds, are invisible to us for thousands of years. Even with advanced telescopes that can peer into the farthest reaches of the disk, we are constantly observing history in transit, never the present moment. The galaxy, in this sense, is a living museum, where every photon is a messenger from the past, carrying the story of stellar evolution across immense stretches of space-time. The perspective of light-speed travel also illuminates the contrast between human-scale distances and galactic distances. Consider that the nearest star beyond the Sun, Proxima Centauri, is only 4.24 light-years away, which is already mind-boggling in everyday terms. Crossing this tiny fraction of the Milky Way would take just over 4 years at light speed. Yet the full journey across the galactic diameter, 100,000 light-years, is more than 23,500 times longer than that trip. Our solar system, which is a minuscule speck in this vast disk, would need eons to traverse even a fraction of the distance that defines the Milky Way's size. The scale is so extreme that standard human analogies, such as traveling by car, plane, or even spacecraft, fail utterly. The galaxy is not just large. It operates on dimensions where time itself stretches beyond human comprehension. This immense timescale also reinforces the isolation of regions within the galaxy. For instance, stars on opposite sides of the Milky Way are effectively disconnected. The light from one edge takes longer than the entire lifespan of most civilizations to reach the other. Even in terms of potential communication or travel, the galaxy is a realm of practical impossibility. If humanity attempted to send a probe across the Milky Way at the speed of light, it would take 100,000 years to arrive, and that's assuming perfect conditions without the obstacles of gravity, dust, or the limitations of matter traveling near light speed. This perspective underscores not only the size, but the intrinsic solitude of our galactic neighborhood. Furthermore, the speed of light framework allows us to appreciate the scale of galactic structures beyond simple linear distance. The spiral arms, the halo, the bulge, and the scattered clusters of stars each extend over tens of thousands of light-years. Traveling from one arm to another, or from the disk to the halo, still requires light-years of time, meaning that even at ultimate speed, the galaxy is more like an expansive continent than a contained system. The orbital paths of stars, taking hundreds of millions of years to circle the galactic center, are minuscule when compared to the journey of a photon crossing the galaxy from one extreme to another, highlighting the staggering difference between stellar motion and the constant march of light across space. From this perspective, the Milky Way is not merely large, it is temporally immense. Light, the fastest traveler in the universe, becomes almost painfully slow when confronted with the vastness of our galaxy. Observing events from across the disk is equivalent to looking back tens of thousands of years into the past. Each photon a bridge spanning eons. The galaxy's enormity thus encompasses both space and time, forcing us to reframe our understanding of scale in a way that challenges intuition and emphasizes the smallness of human experience. Even our position within the galaxy emphasizes this perspective. At 27,000 light-years from the galactic center, the Sun completes an orbit every 230 million years. Yet light from the other side of the galaxy has been traveling for over 100,000 years, long before humans walked the Earth. The contrast between stellar lifetimes, light-speed travel, and galactic dimensions illustrates the staggering scale of cosmic phenomena. No single human lifespan, civilization, or even species can witness the journey of light from one edge of the galaxy to the other. It is a scale reserved for the universe itself, a reminder of our position in a cosmos where time and space are truly infinite relative to our existence. The Milky Way's most visually striking feature, at least from the outside, is its system of spiral arms. These immense curving lanes of stars, gas and dust sweep outward from the central bulge, winding gracefully around the galaxy like the arms of a cosmic pinwheel. While we cannot view the Milky Way from a distance due to our position within one of its arms, astronomers have pieced together its structure using star mapping, radio surveys, and observations of similar spiral galaxies. What emerges is a pattern both elegant and functional, a network of spiral arms that serve as the main highways of star formation, dense with stellar nurseries and glowing clusters. The spiral arms are not uniform in width or density. Some arms, such as the Perseus Arm and the Scutum Centaurus Arm, are broad, containing billions of stars and vast molecular clouds capable of birthing new stars. Others, like the Orion Arm, where our Sun resides, are smaller and less densely populated, yet they play a critical role in shaping the galaxy's overall structure. These arms are dynamic, not static. They are waves of higher density that travel through the galaxy, compressing gas and dust as they move, triggering bursts of star formation along their paths. This spiral pattern is a natural consequence of the galaxy's rotation combined with gravitational forces, creating a rhythm in which stars are born, evolve, and die over millions of years. Within the spiral arms, the concentration of stars and interstellar matter is dramatically higher than in the regions between them. This explains why star formation is heavily localized to these arms, and why the Milky Way appears brighter along their trajectories when viewed in certain wavelengths. In addition to stars, the arms are rich in nebulae, the colorful clouds of gas and dust that glow under the radiation of young, hot stars. Observing these regions, astronomers find countless star clusters at various stages of development, from dense protostellar cores where stars are forming to open clusters of young stars just beginning their lives. The arms are, in essence, the Milky Way's engines of renewal, constantly generating new stars and planets while recycling matter from older stars that have expired. The geometry of the spiral arms is also remarkable. The arms wind around the galactic center in logarithmic spirals, curving gracefully rather than forming perfect circles. This spiral design is not arbitrary. It results from a combination of the galaxy's rotation and the gravitational influence of massive structures, such as the central bulge and dark matter halo. The number of arms and their precise structure have been subjects of debate among astronomers, partly because our vantage point within the galaxy makes direct observation challenging. However, through radio measurements of hydrogen gas and precise mapping of star positions with instruments like the Gaia satellite, scientists have confirmed the general spiral pattern, revealing the majestic sweep of arms that define the galaxy's appearance. The Orion Arm, where our Sun resides, is a relatively minor arm compared to others, but remains critical to our understanding of the galaxy. It is about 3,500 light-years wide and 10,000 light-years long, a narrow lane embedded within the Milky Way's greater spiral structure. Within this arm lie countless stars, star-forming regions like the Orion Nebula, and molecular clouds that will eventually produce future generations of stars. Being situated in this arm, we are effectively located within one of the less crowded suburbs of the galaxy, far from the dense central bulge and the massive star-forming regions that characterize larger arms. This location provides a relatively calm environment, allowing life to emerge on Earth without the threat of frequent nearby supernovae or gravitational disturbances. The spiral arms also play a role in the galaxy's overall rotation. Stars and gas within the arms orbit the galactic center, but the arms themselves move as density waves rather than rigid structures. This means that individual stars move in and out of the arms over millions of years, entering regions of higher density where star formation is active and then leaving them behind. This dynamic process ensures that the arms remain long-lived structures, constantly reshaped by the motions of stars and gas. They are both a structural feature and a temporal one, a pattern frozen into the galaxy's rotation while simultaneously evolving over cosmic time. Beyond their function as sites of star formation, the spiral arms are also visually and scientifically significant because they provide a framework for understanding the galaxy's composition and mass distribution. By studying the distribution of stars and gas within the arms, astronomers can infer the presence of dark matter, understand the dynamics of the galactic disk, and even trace the history of past galactic mergers. Some arms may be remnants of interactions with smaller galaxies that the Milky Way absorbed in the past, evidence that the spiral pattern is shaped not only by internal forces, but also by cosmic encounters over billions of years. Inter-arm regions, often called the galaxy's interior voids, are less dense but still filled with stars and diffuse gas. These areas offer a stark contrast to the bustling activity of the arms. In these quieter zones, older stars dominate, and new star formation is less common. Yet even these regions are not empty. They are threaded with streams of stars from dissolved star clusters, the remnants of smaller galaxies, and faint molecular clouds. The interplay between the dense spiral arms and the more tenuous inter-arm regions creates a complex and layered galaxy, rich in structure and activity across its entire span. Viewed from above, the Milky Way's spiral arms would appear as a vast pinwheel, the central bulge glowing brightly at its center, arms spiraling outward like luminous ribbons, and the halo stretching invisibly around the entire system. From our position within one of these arms, we see only a slice of this grand design, a glowing band of stars arcing across the night sky, giving little hint of the broader structure in which we are embedded. Yet through careful observation and mapping, astronomers have been able to piece together this cosmic jigsaw, revealing the Milky Way as an intricately patterned spiral galaxy, its arms stretching tens of thousands of light years and holding within them billions of stars, gas clouds, and nebulae. The spiral arms are more than just a structural feature. They are the very lifeblood of the galaxy, guiding the formation of stars, distributing gas and dust, and influencing the orbits of countless stellar systems. Without them, the Milky Way would lack both the visual elegance and the dynamic processes that make it a living, evolving galaxy. They are a reminder that even in a universe defined by vast emptiness, structure emerges, patterns form, and life can find its place amid the stars. Our Sun, with all its planets, asteroids, comets, and the life-bearing Earth among them, occupies a relatively quiet corner of the Milky Way. It is positioned about 27,000 light-years from the galactic center, nestled comfortably within the Orion Arm, a minor spiral arm that winds between the larger Perseus and Sagittarius arms. This location places us neither too close to the tumultuous, star-dense bulge at the center, nor at the galaxy's outermost edges, providing a gravitationally stable environment that has likely contributed to the long-term stability required for life on Earth to evolve. The distance from the galactic center is not merely a number. It is a protective buffer that shields our solar system from the high radiation levels and intense gravitational forces that dominate the core regions. The Orion Arm, also referred to as the Orion Cygnus Arm, is a relatively narrow and less populated segment of the Milky Way's disk. Despite its smaller size compared to major arms like Perseus or Scutum Centaurus, it is far from empty. Within its 3,500 light-year width and 10,000 light-year length, the arm contains countless stars, stellar nurseries, molecular clouds, and open clusters, creating a dynamic, active environment that nonetheless lacks the extreme density and radiation levels of the inner galaxy. This makes it an ideal region for the formation and sustenance of planetary systems. Our Sun's location here is somewhat of a cosmic sweet spot, far enough to avoid catastrophic events common in the crowded center, but close enough to benefit from the spiral arm supply of gas and dust, essential ingredients for planet formation. The Sun is moving along the Orion Arm in an orbit around the Milky Way's center, traveling at an average speed of roughly 800 to 28,000 kilometers per hour. Completing a single orbit takes about 230 million years, a journey astronomers call a galactic year. Over its 4.6 billion year lifetime, the Sun has circled the galaxy nearly 20 times, carrying the solar system through different environments and interstellar neighborhoods, each with varying densities of stars and gas clouds. This slow, steady motion through the arm has allowed the solar system to avoid catastrophic encounters with dense clusters or massive stars that might have disrupted planetary orbits or subjected Earth to lethal radiation bursts. Our position within the Orion Arm also provides a unique perspective on the structure of the Milky Way. Because we are embedded in this arm, we see the galaxy as a flattened, glowing band stretching across the night sky, rather than as a fully formed spiral galaxy from above. Observations of nearby stars, molecular clouds, and the distribution of gas help astronomers map the Orion Arm's boundaries and its relationship to neighboring arms. Surveys using radio waves, infrared light, and precise astrometric measurements from instruments like Gaia have revealed not only the local layout, but also the broader spiral structure of the Milky Way, highlighting our place as just one small system among billions in a vast, intricate network of stars. Being 27,000 light-years from the center also defines the environment in which the Sun formed. The chemical composition of stars varies depending on their proximity to the galactic center. Closer to the center, stars are enriched with heavier elements due to generations of supernovae and intense star formation, whereas in the outer regions, stars tend to be more metal-poor. The Sun's location within the Orion Arm places it in a relatively moderate zone, allowing it to inherit enough heavy elements to form rocky planets, asteroids, and the complex chemistry needed for life, without being too close to the violent stellar activity that dominates the inner galaxy. From this position, our solar system is also part of a complex interplay between the local stellar neighborhood and the broader galaxy. Nearby stars, such as those in the Hyades and Pleiades clusters, reside within a few hundred light-years, while dense regions of star formation lie several thousand light-years away. As the Sun orbits the galaxy, it slowly drifts relative to these stars and clouds, encountering varying environments over millions of years. Some of these encounters may influence the Oort cloud, potentially sending comets into the inner solar system, while others may have little noticeable effect. Over cosmic timescales, our journey through the Orion Arm is both a voyage through time and space, exposing the solar system to a variety of galactic phenomena. The Sun's placement within the Orion Arm also provides observational advantages. Because we are neither too close nor too far from dense star-forming regions, astronomers can study both nearby and distant parts of the Milky Way. We can observe neighboring arms, the galactic center, and the halo, piecing together the galaxy's structure and history. Without this advantageous location, much of our detailed knowledge of the Milky Way's spiral structure, stellar populations, and dynamics would be far more limited. Our vantage point is both humble and strategically perfect, giving us a front-row seat to the galaxy's grand design, while keeping us safe from its most dangerous environments. The quiet stability of the Orion Arm and the Sun's orbit through it have been essential for the development of complex life on Earth. Had the solar system formed closer to the central bulge, frequent supernovae, intense radiation, and gravitational disruptions could have prevented life from ever taking hold. Conversely, if it had formed in the sparse outer reaches of the galaxy, the lower density of stars and heavy elements might have limited planet formation and chemical complexity. The Sun's position, therefore, is more than just a point on a map. It is a consequence of a delicate balance within the Milky Way, one that allows the solar system to exist as a stable, life-supporting environment for billions of years. The Milky Way is not a static entity. It is a vast, dynamic system in perpetual motion. Like a giant, spinning disk of stars, gas, dust, and dark matter, it rotates around its center, with stars in the inner regions completing orbits more quickly than those further out. Our Sun, positioned about 27,000 light-years from the galactic center on the Orion Arm, participates in this colossal dance, traveling at an average speed of roughly 828,000 kilometers per hour. At this incredible velocity, the solar system completes a full orbit around the Milky Way's center approximately every 230 million years, a period known as a galactic year. This means that since the Sun's formation 4.6 billion years ago, it has circled the galaxy nearly 20 times, journeying through different stellar neighborhoods, spiral arms, and interstellar environments. The rotation of the Milky Way is a complex phenomenon governed by the interplay of gravity, mass distribution, and dark matter. While the central bulge rotates quickly due to its dense concentration of stars, the outer regions rotate more slowly, creating what astronomers call a differential rotation. This means that stars closer to the center complete orbits faster than those farther away, preventing the galaxy from collapsing inward while simultaneously maintaining its spiral structure. The differential rotation also contributes to the formation and maintenance of spiral arms as density waves, compressing gas and dust to trigger star formation as they sweep through the disk. In essence, the galaxy's rotation is both a stabilizing mechanism and a driver of its structural evolution. As the solar system orbits the galactic center, it travels through regions of varying star density and interstellar matter. Within the spiral arms, the density of stars and molecular clouds is higher, increasing the likelihood of encounters with nearby stars or interstellar objects. Between the arms, the solar system moves through quieter, less dense regions, dominated by older stars and diffuse gas. These varying environments influence the solar system in subtle but significant ways. For instance, gravitational interactions with passing stars can perturb the distant Oort cloud, potentially sending comets toward the inner solar system. Over the course of a single galactic orbit, the solar system experiences a wide range of cosmic conditions, some benign and others potentially disruptive. The journey through the galaxy is also a journey through time. While the solar system completes one orbit every 230 million years, this timescale is comparable to major biological and geological cycles on Earth. For example, the formation and breakup of supercontinents, mass extinctions, and evolutionary radiations have all occurred over periods comparable to the duration of one or more galactic years. This coincidence suggests a subtle connection between the solar system's motion through the Milky Way and the conditions on Earth, as the local galactic environment may influence cometary influx, cosmic radiation, and even the distribution of interstellar gas and dust. Although the connections are complex and indirect, the solar system's orbit is not just a matter of cosmic mechanics. It has potential implications for life and planetary evolution. The mechanics of this orbit are fascinating in their own right. The Sun's path around the galaxy is not a perfect circle, but an elliptical orbit with slight vertical oscillations, moving up and down relative to the galactic plane. These oscillations, taking roughly 60 million years per cycle, cause the solar system to pass through varying densities of interstellar gas and dust, as well as occasional encounters with star-forming regions. Such oscillations may have consequences for cosmic ray exposure and the dynamics of the Oort cloud, influencing the rate at which comets enter the inner solar system. The solar system's trajectory is therefore a three-dimensional journey, weaving through the galaxy's disk, spiral arms, and gravitational influences, rather than a simple two-dimensional circle. The rotation of the Milky Way also explains why stars within the galaxy exhibit different relative motions. While the Sun orbits at a relatively steady speed, other stars may travel faster or slower depending on their location and the gravitational influence of nearby masses. This differential motion leads to phenomena such as stellar streams, tidal tails, and the gradual redistribution of stars throughout the disk over billions of years. In this way, the galaxy is not a static backdrop, but a constantly evolving environment, with stars and star clusters migrating, interacting, and reshaping the structure of the Milky Way over cosmic timescales. From our vantage point, the movement of the Milky Way is imperceptible in real time. Yet over millions of years, it defines the solar system's position relative to the rest of the galaxy. The orbit through the Orion Arm ensures that the solar system is continuously moving, never remaining in one location for long in cosmic terms. It has passed through dense star-forming regions, areas of intense radiation, and relatively empty stretches of space, each contributing to the conditions experienced on Earth. The solar system's constant motion is a reminder that nothing in the galaxy is truly fixed. Even seemingly stable stars like the Sun are part of a dynamic, rotating system spanning over 100,000 light-years. The rotation of the Milky Way and the solar system's journey within it also highlight the interplay between visible and invisible forces. While stars and gas clouds follow predictable orbital patterns, the presence of dark matter adds an additional gravitational component that influences rotational velocities and stabilizes the galaxy's outer regions. Without this unseen mass, the galaxy would not rotate as it does. Stars in the outer disk would move more slowly than observed, potentially leading to the collapse of spiral arms or other structural instabilities. Thus, our orbit is governed not only by the visible mass of stars and gas, but also by the invisible scaffolding of dark matter that dominates the Milky Way's total mass. The vastness of these galactic journeys also underscores the limitations of human perception. While we may measure the solar system's orbital speed and estimate the time it takes to complete a galactic year, these numbers are almost impossible to fully internalize. 230 million years is beyond human comprehension, dwarfing the span of civilizations, species, and even geological eons. Our solar system, while moving at nearly 1 million kilometers per hour, is still traversing only one small part of the Milky Way, emphasizing both our relative insignificance and our fortunate position within a stable orbital path that has allowed life on Earth to flourish. When we step back and look at the Milky Way in the broader context of the universe, its size becomes both impressive and relatively modest. With a diameter of roughly 100,000 to 120,000 light-years, it is far larger than many galaxies in the cosmos, yet it is still dwarfed by giants like the Andromeda galaxy, which stretches over 220,000 light-years across. In comparison to dwarf galaxies such as the Sagittarius dwarf or the Large Magellanic Cloud, the Milky Way is overwhelmingly massive, containing billions of stars, expansive spiral arms, and a central bulge that dwarfs the entire stellar content of its smaller companions. These comparisons help illustrate the diversity of galactic forms and scales, showing that while the Milky Way is a cosmic heavyweight among common spiral galaxies, it is far from the largest galaxy in the universe. Dwarf galaxies, by contrast, are small, often irregularly shaped collections of stars and gas that orbit larger galaxies like the Milky Way. The Large Magellanic Cloud, for example, is only about 14,000 light-years in diameter, less than 1/8 the width of our galaxy. These smaller galaxies may contain only a few billion stars, compared to the Milky Way's 100 to 400 billion. Yet they are crucial components of the cosmic ecosystem. Dwarf galaxies are often the building blocks of larger galaxies, providing material through collisions and mergers that gradually grow the size and complexity of galaxies, like the Milky Way, over billions of years. Their presence around our galaxy illustrates not only scale differences, but also the dynamic and hierarchical nature of cosmic structures. On the other end of the scale, giant galaxies like Andromeda dominate the conversation in terms of sheer size and mass. Andromeda's disk is more than twice as wide as the Milky Way, and its estimated 1 trillion stars make it not just larger, but more densely packed than our home galaxy. Despite the Milky Way's impressive spiral arms and vibrant stellar population, Andromeda's mass and size position it as a rival, almost like a superpower in the cosmic neighborhood. Yet even Andromeda's enormity is dwarfed by some of the truly colossal elliptical galaxies in the universe, which can span millions of light-years and contain tens of trillions of stars. By comparison, the Milky Way, while grand, occupies a middle tier in the hierarchy of galactic scales. These comparisons are not merely academic. They help astronomers understand galactic evolution. The Milky Way's size relative to its neighbors affects gravitational interactions, orbital dynamics, and even the future trajectory of our galaxy. Smaller dwarf galaxies are gravitationally bound to the Milky Way, slowly merging into it and contributing stars, gas, and dark matter. These interactions may influence star formation rates, the structure of spiral arms, and the growth of the central bulge over billions of years. Meanwhile, interactions with a galaxy of Andromeda's magnitude, which is on a collision course with the Milky Way, will reshape both galaxies entirely, transforming their spiral structures and redistributing vast amounts of matter. The diversity of galaxy sizes also highlights how the Milky Way fits into the cosmic tapestry. Its mass, diameter, and stellar population place it comfortably in the category of large spiral galaxies, like many others scattered across the universe. It is significantly larger than the majority of dwarf galaxies, but smaller than the giants that dominate galaxy clusters. This positioning explains why the Milky Way has a retinue of satellite galaxies. Its gravitational pull is strong enough to capture and retain smaller companions, while still being dwarfed by the largest galaxies that exist. The presence of these companions, ranging from the Magellanic Clouds, to more distant dwarf spheroidals also illustrates the hierarchical structure of the universe, in which galaxies grow through mergers and accretion. Comparing sizes also gives perspective on galactic structure. While the Milky Way's diameter is impressive, its thickness is relatively modest at roughly 1,000 light-years, making it a thin, flat disk compared to some of the more spherical, elliptical giants. This thinness contributes to the prominence of spiral arms and the concentration of star-forming regions within the disk. Dwarf galaxies, by contrast, often lack coherent spiral structure, with stars dispersed more irregularly, while giant galaxies may exhibit densely packed cores and halos of stars that extend far beyond their visible disks. In this sense, the Milky Way is balanced, large enough to sustain complex structure and active star formation, yet not so massive that it becomes a chaotic, overly dense environment. In terms of mass, the Milky Way is estimated to contain about 1.5 trillion solar masses, most of it in the form of dark matter. While this dwarfs the visible matter in smaller galaxies, it is only a fraction of the mass contained in the largest galaxies, which may reach 10 trillion solar masses or more. The gravitational influence of the Milky Way, therefore, is substantial in its local cosmic neighborhood, shaping the orbits of nearby dwarf galaxies, controlling satellite systems, and interacting with neighboring spirals like Andromeda. Yet, when scaled against the vastest galaxies in the universe, our home is still one player among many in a crowded cosmic landscape. Even visually, the difference is striking. From a distance, a dwarf galaxy like the Sagittarius dwarf might appear as a faint smudge of stars, barely distinguishable from the cosmic background, whereas Andromeda shines as a bright, sprawling disk, visible to the naked eye under dark skies. The Milky Way, observed externally, would be somewhere between these extremes, a prominent spiral galaxy with glowing arms, a central bulge, and a halo of stars and dark matter that commands attention but doesn't overwhelm. Within this spectrum, our galaxy is remarkable not for being the largest, but for being an elegant, structured, and active spiral, capable of sustaining complex systems like the solar system. Understanding these comparisons also provides insight into our galactic future. The Milky Way's size relative to Andromeda explains why the two galaxies are on a collision course. Their mutual gravitational attraction will draw them together over the next 4 billion years, ultimately merging into a massive elliptical galaxy. Dwarf galaxies, on the other hand, are gradually being absorbed by the Milky Way, their stars assimilated into the disk and halo over time. These interactions highlight how size determines not only a galaxy's present structure, but also its destiny, influencing both the scale and type of mergers it experiences. The contrast between the Milky Way and other galaxies, from tiny dwarfs to immense giants, is also a reminder of the diversity of the universe. Galaxies can range from a few thousand light-years in diameter to over 1 million, containing anything from a few million stars to tens of trillions. Within this spectrum, the Milky Way stands as a significant but not extreme example, large enough to host complex structures and billions of stars, yet not so colossal as to be anomalous. This perspective helps contextualize our place in the universe. Our galaxy is grand, but it is one of countless others, each with its own scale, structure, and story. In the vast timescales of the cosmos, the Milky Way is not destined to remain unchanged. In about 4 billion years, our galaxy is on a collision course with the Andromeda galaxy, a neighboring spiral that currently dominates the local group alongside the Milky Way. Traveling toward us at roughly 110 kilometers per second, Andromeda is inexorably drawing closer, and over the course of billions of years, the two colossal spirals will collide, interact, and ultimately merge. This event, though cataclysmic on galactic scales, is unlikely to cause direct collisions between stars, as the distances between individual stars are immense. Yet, the gravitational forces at play will dramatically reshape the structure of both galaxies, triggering bursts of star formation and fundamentally transforming the appearance of our cosmic home. The merger will begin as the outskirts of the two galaxies brush against each other, with tidal forces stretching and distorting the spiral arms into long, luminous streams of stars and gas. These tidal tails, composed of stars torn from their original orbits, will arc across the void between the galaxies, creating an intricate web of stellar debris. As the galaxies pass through each other multiple times, gravitational interactions will funnel gas toward the central regions, feeding bursts of star formation that can outshine entire sections of the galaxies. These so-called starburst events will create clusters of new stars, many of them massive and short-lived, dramatically altering the composition and luminosity of the galaxies. Over the ensuing billions of years, the cores of the Milky Way and Andromeda will spiral inward, gradually merging into a single, more massive galaxy. The supermassive black holes at the centers of each galaxy, including Sagittarius A at the heart of the Milky Way, are expected to coalesce eventually, forming an even more enormous black hole with gravitational influence extending far beyond the original bulges. This central merger will dominate the dynamics of the new galaxy, pulling stars and gas into tightly bound orbits while ejecting some material into intergalactic space. The result will be a massive elliptical or lenticular galaxy, sometimes nicknamed Milkomeda, which will represent the ultimate fusion of these two stellar metropolises. While the collision will dramatically restructure the Milky Way, the odds of catastrophic events on a stellar or planetary scale are surprisingly low. Stars are separated by vast distances, meaning direct impacts between them are extremely unlikely. Nevertheless, the gravitational perturbations will likely alter the orbits of many stars, potentially sending some into highly elliptical paths or even ejecting them from the newly formed galaxy. Solar systems, including our own, may experience changes in stellar neighbors or minor shifts in orbital dynamics. But life on Earth, assuming it still exists, would have a front-row view of an unprecedented celestial show. Over the eons, the night sky will transform from the familiar Milky Way band to a chaotic, brilliant mix of stars and gas clouds drawn from both galaxies, culminating in a smooth, luminous, elliptical galaxy once the merger stabilizes. The Andromeda-Milky Way collision also provides a powerful illustration of cosmic time and scale. Even at millions of kilometers per hour, the galaxies will take billions of years to fully merge. The process is slow, imperceptible on human timescales, yet inevitable from the perspective of astrophysics. This demonstrates the immense patience of cosmic evolution, where even catastrophic events unfold gradually, allowing stars, planets, and stellar systems to continue orbiting relatively undisturbed for vast spans of time. Each phase of the collision, from initial approach to final stabilization, is governed by the interplay of gravity, mass distribution, and dark matter, creating a complex ballet that reshapes matter on a galactic scale. Astronomers have modeled this future collision extensively, using computer simulations that account for the gravitational influence of both visible and dark matter. These simulations reveal intricate patterns of star streams, gas compression, and angular momentum transfer, predicting the formation of new structures that never existed in either progenitor galaxy. They also indicate that the spiral arms, so characteristic of both galaxies today, will be disrupted, winding tighter and eventually dissolving into the smooth stellar distribution characteristic of large elliptical galaxies. Over the next several billion years, the Milky Way will lose its familiar pinwheel shape, merging into a more uniform, spheroidal structure where the remnants of its spiral arms are barely discernible. The collision will also have profound implications for satellite galaxies and the surrounding cosmic environment. Dwarf galaxies orbiting the Milky Way and Andromeda will be pulled into the gravitational maelstrom, either merging with the new galaxy or being flung into intergalactic space. Streams of stars and gas will extend far beyond the central regions, contributing to an expanded halo that may dwarf the original halos of either galaxy. This event emphasizes that galaxies are not isolated entities, but dynamic systems that grow, evolve, and interact over billions of years. The merger is a natural step in the Milky Way's life cycle, illustrating how even seemingly stable galaxies are transient on cosmic timescales. From a human perspective, this future collision is a reminder of the vastness of time compared to the brevity of individual lives. 4 billion years is so far into the future that imagining it requires thinking on a scale utterly alien to human experience. By then, Earth itself may be uninhabitable due to the Sun's evolution, yet the galaxy will continue its slow, inexorable transformation. The stars we see today, the familiar constellations, and even the solar system itself may all be rearranged or dispersed, yet the cosmic dance will continue, highlighting the eternal motion and evolution inherent in galaxies. Ultimately, the impending Milky Way-Andromeda merger is a powerful testament to the dynamic nature of the universe. It reminds us that galaxies are not eternal, static structures, but evolving systems shaped by gravity, collisions, and cosmic time. The Milky Way, magnificent as it is now, will one day become part of a larger entity, continuing the cycle of formation and transformation that defines the cosmos. Observing this process, even in simulation, allows humanity to grasp the immense scales of distance, mass, and time involved in galactic evolution, emphasizing both our smallness and the extraordinary beauty of the universe's ongoing story. Measuring the Milky Way is no simple task. Unlike many objects in the universe that can be observed from a distance, we are embedded within the galaxy itself, making it difficult to gain a full perspective of its shape and size. To overcome this challenge, astronomers employ a variety of sophisticated techniques, combining observations of stars, gas, and other forms of radiation to construct an accurate map of the galaxy. One of the primary tools in this endeavor is star mapping. By cataloging the positions, motions, and distances of millions of stars, astronomers can infer the structure of the spiral arms, the extent of the disk, and the distribution of stars within the galactic bulge. These detailed maps help create a three-dimensional understanding of the Milky Way, revealing not only where stars are located, but also the large-scale patterns they form. In addition to visible stars, radio waves play a critical role in mapping the galaxy. Hydrogen, the most abundant element in the Milky Way, emits a specific radio signal known as the 21-centimeter line. By detecting this emission across the sky, astronomers can trace the distribution of hydrogen gas, which is closely linked to star-forming regions and spiral arm structures. This technique allows researchers to peer through dust clouds that obscure visible light, providing a more complete view of the galaxy's architecture. Observations of molecular clouds, masers, and other radio sources further refine our understanding of distances and dynamics within the Milky Way, enabling precise measurements of rotational velocities and the overall mass distribution. Space-based telescopes have also revolutionized the measurement of the Milky Way. One of the most transformative instruments is the Gaia satellite, launched by the European Space Agency. Gaia has mapped the positions, distances, and motions of over 1 billion stars with unprecedented accuracy. By analyzing this vast data set, astronomers can identify the precise shape of the spiral arms, measure the thickness of the disk, and determine the size of the central bulge. Gaia's ability to track stellar motion in 3 dimensions allows for the calculation of the Milky Way's rotation curve, providing insights into both visible and dark matter. This data also helps in understanding how stars migrate over time, revealing the dynamic processes that have shaped the galaxy throughout its history. Beyond individual stars and gas clouds, astronomers also use gravitational effects to measure the galaxy's size and mass. The motion of stars and satellite galaxies around the Milky Way provides clues about the underlying distribution of matter, including the elusive dark matter halo that extends far beyond the visible disk. By analyzing how these objects move under gravity, researchers can estimate the total mass of the galaxy, which in turn informs estimates of its full spatial extent. This method is crucial because the visible stars alone do not account for the majority of the galaxy's mass. Much of it is invisible, yet it profoundly influences the Milky Way's rotation and structure. Infrared astronomy has added yet another layer of understanding. Infrared light penetrates the dense dust that obscures much of the galaxy in visible wavelengths, allowing astronomers to study regions near the galactic center and within spiral arms. Instruments such as the Spitzer Space Telescope have provided high-resolution infrared maps revealing star-forming regions, the structure of the central bulge, and the distribution of older stars throughout the disk. By combining infrared data with radio and optical observations, scientists can construct a comprehensive multi-wavelength picture of the Milky Way, bridging gaps that any single method alone could not fill. Parallax measurements, another fundamental technique, also play a critical role. By observing the apparent shift in a star's position as Earth orbits the Sun, astronomers can calculate its distance with remarkable precision. While this method is limited to relatively nearby stars, combining parallax data with other distance indicators, such as variable stars like Cepheids and R Lyrae, extends our reach across much of the galaxy. These standard candles allow scientists to gauge distances to star clusters, spiral arms, and even the far edges of the galactic disk. The cumulative effect of these techniques is a detailed map that defines the Milky Way's diameter, thickness, and overall stellar distribution. Measuring the galaxy's rotation is another critical aspect of understanding its size. By analyzing the Doppler shifts of stars and gas clouds, astronomers determine how fast different regions of the Milky Way are moving. This information reveals the rotation curve, which shows that stars in the outer disk move at similar speeds to those closer to the center, a discovery that led to the inference of a massive dark matter halo. Understanding these rotational dynamics is essential for accurately estimating the galaxy's total size, as it provides context for how mass and gravity are distributed throughout the Milky Way. Mapping the Milky Way also involves studying its satellite galaxies and stellar streams. Dwarf galaxies orbiting the Milky Way, as well as remnants of past mergers, offer clues about the galaxy's gravitational boundary and overall structure. By tracing these interactions and the distribution of stars stripped from satellite galaxies, astronomers can refine the estimates of the Milky Way's extent. Streams of stars in the halo, detected through deep surveys and precision astrometry, reveal the outermost reaches of our galaxy, often extending far beyond the visible disk. Through the combination of star mapping, radio observations, space-based telescopes like Gaia, infrared imaging, parallax measurements, and the study of gravitational interactions, astronomers have been able to construct an increasingly precise picture of the Milky Way. Each method complements the others, allowing scientists to overcome the challenges of observing a galaxy from within. The result is an understanding not only of the Milky Way's size, its diameter, thickness, and halo, but also of its dynamic structure, rotational behavior, and the distribution of both visible and dark matter. These measurements are crucial for understanding our place in the cosmos, as they provide the context in which the solar system exists and the scale against which the vastness of the galaxy can be appreciated. Beyond the luminous stars, glowing nebulae, and dense clouds of gas that define the Milky Way's visible structure, there exists a vast and mysterious component of the galaxy that remains invisible to the eye and most traditional instruments: dark matter. This enigmatic substance, which neither emits nor absorbs light, cannot be detected directly, yet its gravitational influence is undeniable. Observations of the Milky Way's rotation curve, how stars and gas clouds move at different distances from the center, revealed that the outer regions of the galaxy rotate far faster than expected based solely on the mass of visible matter. Without the additional gravitational pull from a massive, unseen component, these stars would escape the galaxy entirely. This invisible mass, now known as the dark matter halo, dramatically extends the Milky Way's true size, far beyond the disk that we can observe with telescopes. The dark matter halo envelops the galaxy like an immense spherical cocoon, stretching hundreds of thousands of light years into space. While the visible disk measures roughly 100,000 to 120,000 light years across, the dark matter halo may extend 2 to 3 times farther, reaching up to 300,000 light years from the galactic center. Its density is highest near the core and gradually decreases with distance, creating a gravitational well that holds the galaxy together. Without this halo, the Milky Way's outer stars, along with many of its satellite dwarf galaxies, would be gravitationally unbound, drifting away into intergalactic space. The presence of dark matter ensures the galaxy maintains its structure, stabilizes its rotation, and provides the gravitational scaffolding upon which the luminous matter rests. Although invisible, the dark matter halo can be studied indirectly through its effects on stars, gas clouds, and satellite galaxies. Precise measurements of orbital velocities, stellar streams, and the motion of globular clusters reveal the halo's mass distribution. These studies indicate that dark matter constitutes roughly 85% of the total mass of the Milky Way, dwarfing the combined mass of stars, gas, dust, and the central black hole. By comparing the observed motions of celestial objects with theoretical models, astronomers can map the halo's extent and density profile, providing insight into both the Milky Way's size and the fundamental nature of dark matter itself. The halo is not uniform. It contains clumps and filaments that reflect the Milky Way's dynamic history of mergers and accretion. Many of the halo's stars and gas originated in smaller galaxies that were gravitationally captured and absorbed over billions of years. These remnants form stellar streams and substructures scattered throughout the halo, each telling the story of past interactions. By studying these features, astronomers can reconstruct the Milky Way's assembly history, gaining insight into how galaxies grow and evolve over cosmic time. The halo is thus both a physical and historical extension of the galaxy, preserving evidence of interactions that shaped its current form. Dark matter also plays a critical role in the interaction of the Milky Way with other galaxies. Its extended halo is the first point of contact in gravitational encounters, influencing orbital paths, tidal forces, and eventual mergers. For example, the anticipated collision with the Andromeda galaxy in about 4 billion years will be significantly affected by the overlapping halos of dark matter, which will interact long before the stars themselves collide. The gravitational pull of the halo governs the trajectories of the two galaxies, accelerates the merger process, and affects the redistribution of stars, gas, and dust during the collision. In this sense, the halo is both a stabilizing force in the present and a determinant of the Milky Way's future. The existence of a dark matter halo also challenges our understanding of physics and the universe at large. While its gravitational effects are well documented, its composition remains unknown. Leading theories suggest it consists of exotic, weakly interacting particles that permeate space, yet elude direct detection. Some hypotheses propose alternative explanations, such as modifications to the laws of gravity at galactic scales, but these remain speculative. Regardless of its nature, the dark matter halo fundamentally redefines the scale of the Milky Way. The galaxy is far more massive and extensive than visible observations alone would suggest, encompassing a region of space dominated by unseen matter. The halo's invisible reach has profound implications for our perception of the Milky Way's size. When considering only the disk of stars and gas, the galaxy may seem vast, stretching over 100,000 light-years. Yet, when the dark matter halo is included, the gravitational influence of the Milky Way extends much farther, enveloping distant stars, globular clusters, and satellite galaxies. It transforms our understanding of galactic boundaries. The Milky Way is not just the disk of visible matter, but a massive gravitational entity, with its influence felt across hundreds of thousands of light-years. This expanded perspective emphasizes that much of the galaxy exists beyond the limits of direct observation, hidden in darkness, but essential to the galaxy's integrity. Furthermore, the dark matter halo is thought to interact with the galaxy in subtle but critical ways. It stabilizes the rotation of the spiral arms, helps maintain the shape of the disk, and provides a gravitational anchor for satellite galaxies. Its presence may even influence the distribution of interstellar gas, affecting star formation rates throughout the Milky Way. By holding the galaxy together, the halo ensures that the intricate spiral structure, central bulge, and disk remain coherent over billions of years, allowing the galaxy to function as a stable, evolving system. Without this invisible component, the Milky Way would appear drastically different, with stars in the outer regions dispersed into intergalactic space, leaving a smaller, less organized galaxy. Studying the dark matter halo also enhances our understanding of the universe beyond the Milky Way. By comparing the halo with those of other galaxies, astronomers can investigate how dark matter influences galaxy formation, mergers, and evolution on a cosmic scale. The halo provides a link between local galactic dynamics and the large-scale structure of the universe, offering clues about the distribution of matter in galaxy clusters, cosmic filaments, and voids. In this sense, exploring the Milky Way's dark matter halo is not just a study of our galaxy's size, but a window into the invisible framework that shapes the cosmos itself. The Milky Way is not alone in the cosmos. It resides within a collection of galaxies known as the Local Group, a gravitationally bound system containing more than 50 galaxies of various sizes and types. While the Milky Way is one of the largest members of this group, it shares its neighborhood with other massive spirals such as the Andromeda galaxy and the Triangulum galaxy, as well as numerous dwarf galaxies orbiting the larger systems. The Local Group spans roughly 10 million light-years across, a vast volume of space in which galaxies interact through gravity, exchanging stars, gas, and dark matter over billions of years. Understanding the Milky Way's position within this group helps astronomers place our galaxy into a broader cosmic context and illustrates how even enormous galaxies are part of a larger interconnected system. Among the Milky Way's closest companions are the Large and Small Magellanic Clouds, two irregular dwarf galaxies visible from the southern hemisphere. These satellites are gravitationally bound to the Milky Way and orbit it while contributing to the overall mass distribution and gravitational dynamics of the galaxy. The Magellanic Clouds contain billions of stars between them, as well as significant amounts of gas and dust, which interact with the Milky Way's halo. Gas streams pulled from these dwarf galaxies, such as the Magellanic Stream, provide a direct pathway for material to flow into the Milky Way, fueling new star formation and altering the galactic environment. These interactions illustrate that the Milky Way's size and structure are not only defined by its internal components, but also by the gravitational interplay with neighboring galaxies. Dwarf galaxies surrounding the Milky Way vary greatly in size, shape, and stellar population. Some, like the Sagittarius dwarf elliptical galaxy, are currently being tidally disrupted, leaving streams of stars that gradually merge into the Milky Way's halo. Others, such as the Fornax or Carina dwarfs, orbit more stably, but still feel the Milky Way's gravitational pull. Studying these satellites provides insight into the dynamics of galaxy formation, the role of dark matter in maintaining structural integrity, and the processes through which large galaxies grow over time. The presence of these dwarfs highlights the hierarchical nature of the universe, where small galaxies often serve as building blocks for larger systems. The local group itself is a dynamic environment. Although the Milky Way and Andromeda dominate in mass and size, the gravitational interactions among the group's members create tidal forces, star streams, and occasional mergers that influence the evolution of each galaxy. The group is not isolated. It forms part of the Virgo supercluster, which contains thousands of galaxies bound together in an even larger cosmic structure. Within this framework, the Milky Way is a significant player, yet it remains only a fraction of the mass and scale of the surrounding supercluster. Observing our galactic neighborhood thus provides a microcosm for understanding how galaxies interact on larger scales across the universe. The spatial relationships between galaxies in the local group also provide insight into the Milky Way's past and future. Evidence of past mergers with dwarf galaxies can be traced in the stellar halo, streams of stars, and globular clusters scattered throughout the galaxy. These remnants reveal a history of accretion, where the Milky Way grew not only through internal star formation, but also by assimilating smaller companions. Looking forward, the local group will continue to evolve, with the Milky Way and Andromeda gradually approaching each other for a merger billions of years from now, while dwarf galaxies will be absorbed or ejected. This ongoing evolution underscores that galaxies are not static islands in space, but active participants in a complex cosmic web of interactions. The Milky Way's gravitational influence extends far beyond the visible disk, reaching into the outer halo and exerting control over nearby satellite galaxies. These interactions shape the distribution of dark matter and stars, allowing astronomers to map the galaxy's extended halo and understand its true size. Streams of stars stripped from dwarfs, as well as gas pulled from companions, provide material that integrates into the Milky Way over time, subtly reshaping its structure and mass distribution. The local group acts as a laboratory for observing these processes in action, offering a closer and more detailed view than is possible with more distant galaxies. Our galaxy's position within this group also informs the study of cosmic evolution. By comparing the Milky Way with other local group members, astronomers can identify common features such as spiral structures, bulges, and halos, while also observing unique differences in mass, composition, and star formation activity. Dwarf galaxies provide clues about the early universe, preserving conditions that may no longer exist in larger systems. Through careful observation of the Milky Way's neighborhood, scientists can reconstruct the history of galaxy formation, understand the role of mergers in building mass, and predict how interactions within the local group will shape the Milky Way's future. When contemplating the Milky Way, it is almost impossible to grasp its sheer scale through the lens of human experience. Our daily lives, confined to the relatively tiny surface of the Earth, seem infinitesimal when set against a galaxy that spans roughly 100,000 to 120,000 light-years across. Even light, the fastest thing in the universe, would take 100,000 years to travel from one edge of the Milky Way to the other, a duration that dwarfs the entire history of human civilization. This vastness is so beyond ordinary comprehension that conventional measures, kilometers, miles, or even astronomical units become meaningless. Instead, we must think in terms of light years, parsecs, and cosmic timescales, tools designed to bridge the staggering gap between human perception and the immense reality of our galactic home. To put the scale into perspective, consider the size of our solar system. If the Sun were reduced to the size of a standard beach ball, the Earth would be a tiny marble orbiting at a few meters away, and the outer planets would be barely visible specks at tens of meters distance. Now, imagine extending this analogy to the Milky Way. The entire solar system is no larger than a grain of sand within a sprawling desert of stars. Each star in the galaxy is itself a sun with its own planetary system, and the galaxy contains between 100 and 400 billion stars, along with gas, dust, black holes, and dark matter. From this perspective, the Earth is almost negligible, a minute component in a grand cosmic tapestry that stretches across unimaginable distances. The spiral arms of the Milky Way further emphasize this enormity. These arms, gracefully winding around the central bulge, stretch tens of thousands of light years from the core, each containing vast clusters of stars and nebulae. Our Sun, residing in the Orion Arm, is but one among billions of stars along a slender filament orbiting the galactic center at approximately 828,000 kilometers per hour. Even over millions of years, our solar system traverses only a small portion of a single arm. These motions remind us that the scale of human life is fleeting and small, an instant in the lifetimes of stars and galaxies. Moreover, the Milky Way's halo, composed of both stars and invisible dark matter, extends far beyond the visible disk, forming a gravitational envelope that reaches hundreds of thousands of light years into space. This halo contains remnants of dwarf galaxies, streams of stars, and unseen mass that together define the galaxy's true size. While these regions may be invisible to the naked eye, they exert a profound influence on the motion of stars and satellites throughout the galaxy. In this sense, much of the Milky Way exists beyond what we can see directly, emphasizing that the galaxy's scale is not limited to the glowing stars we observe, but extends into realms of unseen mass and structure. When we extend this perspective even further, the Milky Way itself is just one of billions of galaxies in the observable universe, each containing similar or even larger structures. Galaxy clusters, superclusters, and cosmic filaments stretch across millions of light years, forming a vast cosmic web that dwarfs even the Milky Way. In this context, the enormity of our galaxy is simultaneously humbling and awe-inspiring. It is immense enough to contain countless stellar systems, yet small when compared to the grand architecture of the cosmos. Human existence, in terms of scale and duration, becomes almost negligible against this backdrop, highlighting both our fragility and our unique vantage point from which to observe and understand the universe. Even if one were to travel at unimaginable speeds, the distances involved are staggering. For instance, if a spacecraft could move at 1/10 the speed of light, it would still require over 1 million years to traverse the Milky Way's disk. Light itself, racing across the galaxy at nearly 300,000 kilometers per second, would take 100,000 years to cross from one side to the other. Such numbers defy intuitive understanding. They cannot be directly experienced or visualized in human terms. They force us to expand our perception, embracing scales of time and space that dwarf the familiar rhythms of daily life and human history. The Milky Way is more than just a collection of stars, gas, and dust. It is our cosmic home, a sprawling island of matter and energy suspended in the vast ocean of the universe. stretching over 100,000 light-years, with hundreds of billions of stars, a dense central bulge, extended spiral arms, and an invisible halo of dark matter. It dwarfs our tiny solar system in ways almost impossible to imagine. Yet, despite its immensity, the Milky Way is only one of billions of galaxies scattered across the observable universe, each with its own stars, planets, and mysteries waiting to be uncovered. Its size, complexity, and dynamic nature remind us that we are part of something far greater than ourselves, a universe filled with structure, motion, and beauty that operates on scales far beyond human comprehension. Standing on Earth and gazing at the night sky, it is humbling to realize that every pinpoint of light is a distant sun, many with their own planetary systems, perhaps harboring worlds as diverse and fascinating as our own. The Milky Way's spiral arms stretch for tens of thousands of light-years. Its halo extends even farther, and its gravitational influence shapes the motions of nearby galaxies. Its rotation, interactions, and eventual future collision with Andromeda illustrate that galaxies are not static monuments, but living, evolving systems. Dark matter, invisible yet pervasive, ensures its cohesion, stretching the galaxy far beyond what we can see, and reinforcing the idea that much of the cosmos remains hidden, waiting for discovery. In contemplating the Milky Way, we confront both the enormity of space and the delicate improbability of life on Earth. Our planet, our solar system, even our entire species occupy only a minuscule fraction of this colossal structure. Yet within this small corner of the galaxy, life has emerged, curiosity has taken root, and consciousness has arisen to reflect on the galaxy itself. The Milky Way is not just an island of stars. It is a stage upon which cosmic processes unfold, a laboratory of creation and transformation, and a reminder of the beauty and complexity inherent in the universe. Ultimately, the Milky Way inspires awe because it connects the intimate and the infinite. It situates us within a vast, interconnected cosmos, offering perspective on our place in space and time. It is a home, a frontier, and a monument to the scale and majesty of the universe, a galaxy beyond imagination, yet one among billions. In its vastness, it humbles and elevates us simultaneously, inviting wonder, exploration, and an ever-deepening appreciation for the universe that surrounds us. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.